My name is Ethan Nan, and this is my Eureka final presentation video. First, a little bit about me. I go to Cupertino High School, and I'm a junior. If you don't know what Cupertino is, it's in the Bay Area, near San Francisco, I guess. It's where Apple headquarters is. In terms of my extracurriculars, I work at a boba shop. It's called Wampo Tea Shop, and I also am on our school tennis team. My interests include cooking, playing tennis, playing video games, as well as listening to music and hanging out with my friends. Now, more about my actual research project itself. The first step was, as always, brainstorming ideas about what to write about. The first idea that I looked at was herd behavior, which is the idea of people following others in a decision, such as if you look at the stock market, a lot of people who don't know a lot, if they see people start selling, they start selling. If people start buying, they start buying. That's what herd behavior is. And it was my first idea on what to analyze. Another topic I was looking into was mahjong. It's a Chinese game played with these tiles you can see in the picture, and it includes strategic decisions. And yeah, it's similar to like a Chinese poker, maybe you could think of, because people bet on it as well. And my third topic was poker. Uh, I just have always found poker to be interesting. I've watched poker, like people play poker professionally a lot, and yeah, I was interested in studying it. So after I started reviewing relevant papers, which I found with the help of my professor. Um, and so after looking through papers, we realized there's not very many papers on mahjong to like look at to begin with. Just a relatively unexplored field. Herd behavior were a lot of papers. Poker also had a lot of papers. And so after looking through those two, I ended up deciding that I preferred poker. And so after doing that, I had to create my own game. Um, because poker itself is a really complicated game. It's very hard to analyze the entirety of poker. So rather than analyzing the actual game of poker, what many people do, including myself, is simplify the game in some way, either by reducing the amount of cards, the amount of actions, something along those lines, and then calculating that like numbers in that game specifically. So in one of the papers that I read, they used three cards, one, two, and three, and limited the amount of actions by every player. And what they found was the optimal uh, like strategy for each player in order to maximize their expected value. And so I decided to try to emulate this by using four card poker instead. And so I started doing my calculations. I did my math similarly to how they did, which you'll see later in my paper. But basically, it includes taking all different cases for the cards people could have. So, say player one has a one and player two has a four, or player one has a one, player two has a three, all those situations, and then uh, taking their expected value based on the decisions you can possibly make in those situations and putting them together to see what the expected value for each player is for a given strategy. Then I started analyzing my calculations, which I put them into a table together. Um, so if one person does these strategies and the other person plays this strategy, like what's the expected value for each player? So like say I play really aggressively and I bet every time I can, and the other player also bets every time they can. How much money am I expected to gain or lose from that situation when I play over a long period of time? And finally, obviously, I organize my results into an actual paper. Challenges. One of my main challenges in this process was that, well, I originally planned on finding the optimal strategy for each player. However, the problems arose when I started doing my calculations, and I found that it was actually quite impossible to simplify what I had and to solve it. The reasoning behind this is because in the original paper I was basing my calculations off of, they had three cards, which actually cuts the amount of cases in half from four cards, and it also makes it so there are less variables, so it actually simplifies out into something you can solve. Whereas, which you'll see in the next slide, is not possible in my paper. So I had to brainstorm ways to get around this problem. And my main solution that I found after a few days of thinking was rather than finding an optimal strategy, how about I just analyze the comparisons between different strategies that like a new player may employ, such as playing really aggressively or really passively or just 50-50, because I'm sure a lot of people do that. It's just a very simple decision, doesn't take too much thinking. Yeah. So what are the results of my paper? Well, here's my paper. In the start, we have abstract, introduction. I'm just introducing what poker is, um, and then like what sections cover what. So in section 2, I analyzed 3 different papers that are fairly relevant to my own paper, including one that calculated a 4-card game, but with much simpler actions than I had. And then this paper was just one I took my inspiration off of, which included 3 cards, but the same amount of actions that my game has. And this last one is a little less relevant, but I found the paper really interesting because it was a calculation of, in normal poker, 52 cards, and 3 cards per player, how much of an impact does having a lot of skill have on the game? Now, in section 3, I define my own game, in which case there are 4 cards, 1 through 4, and the opener has 2 options to either check or bet, and it's a set amount of 100. And assuming the opener checks, then the dealer has to either check as well to check through the round or bet. And if the dealer decides to bet, then the opener has to either fold, giving up the hand, or bet. And yeah, so in section 4, I have my actual game theory analysis, where I actually, this is the lead up to the math and then also the actual math itself. So in here, there's 2 things I define, which are like really stupid mistakes. One being calling with a 1, because if you ever call with a 1, you know you're going to be confronting them in terms of values, and you cannot win with the 1 because 1 is the smallest number. Another mistake would be folding with the 4, as if you fold with the 4, you're just throwing away an opportunity to win money, as it's impossible to lose with the 4. Afterwards, I decided to define these variables. So it goes Q1 all the way to Q5, and then P1 all the way to P6. These are the frequencies of each action for each player. So for example, Q1 is the frequency that that the dealer decides to bluff after they see the opener check. And for example, P4 is the frequency that the opener bets seeing that they have a 4. Now, under here, I define all 12 of my cases. So opener has a 1, dealer has a 2, opener has 1, dealer has a 3. It's all the cards possibilities. And in each possibility, I list out all the possible outcomes. So for example, if the opener has a 4 and the dealer has a 3, the opener will gain $200 if they bet, and the dealer folds, which has this probability of happening based off of these predefined frequencies. Or for example, if both players check, they will also gain $200, and they'll gain 300 if they check and the dealer bluffs, or if they bet and the dealer calls. And under this section, I sum up all the different cases separately. So this is the cases where the opener can lose $100. So in cases 1, 2, 3, 5, 6, and 9, it's possible for the opener to lose money. And here is the cases where the opener can gain $200, and this is the opener can gain $300. It's important to keep in mind that these numbers, in terms of gaining, are assuming that the original $200 in the pot in order to play, also known as the ante, are not included as money from the actual players themselves. It's merely to make calculations a little simpler, because rather than having 4 different possibilities, there's only 3. And underneath, we have expected value. So this is the expected value without including the ante, and this is the expected value including the ante, minus 1, because each of these numbers is technically scaled up in hundreds. So minus $100 of expected value for the player because they had to put in 100 to play the hand in the first place. So when combining the variables and cases together, using this formula, we end up with this jumble of numbers, which simplifies to equal this. The problem here is that it's not very simplifiable, which is what I noticed when I started trying to find an optimal strategy. It's not really possible to summarize this into like a few sections where, if something equals 0, certain numbers cancel out like well. So because of that, I decided to switch gears, as I mentioned earlier, to finding, rather than the optimal strategy, the interactions between opener strategies. So down here I have defined different strategies. For example, for the opener, they can either play aggressively, which means they always bet, they always bluff, or they can play passively. They never bet, never bluff. They always check and fold. Or they could play neutral. Neutral is in like impartial to either strategy. So what they do is they bet 50% of the time, call 50% of the time, and they fold 50% of the time. They do everything 50% of the time. Very even. For the dealer, I included the exact same strategies: aggressively playing, passively playing, and neutrally playing. Afterwards, by taking these numbers and plugging them into this formula here, I came out with these tables. So for the opener's expected value, if they employ strategy 1 and dealer employs strategy 1, then the opener is expected to lose 1/3, which is essentially, if you multiply by 100, $33 every single game. Obviously, you can't lose $33 in a game. You can only lose 100, you can lose 200, you can gain 200, you can gain 100. But this is more of like over a period of time. So say I played 300 games on average in each of game, I would have lost $30. Now I just created another table for the dealer, which is exactly just the opposite of the opener table because it's a zero-sum game. Any money that comes out of one's pocket has to go into the others. And these are the expected values for each different strategy for each player. So if you look at these numbers, you can tell clearly for the dealer, as long as they play D1, they're in a really good position. They're expected to win $50 every time they play. And you can see the dealer is clearly at an advantage in this game because the opener is expected to lose money no matter how they play. So I conclude my paper here, and I note that it's important to keep in mind that in realistic cases, a strategy like always betting, always folding is very unlikely, as it's generally not normal to believe that it's right to just commit to something like that. So the 50-50 situation is much more likely, in which case, if you notice here, actually, it's still slightly advantageous for the dealer, uh, but not as much. Um, and so I conclude my paper with a small note that truly in real life, the best way to play is to notice mistakes in your opponent's play because they're likely not playing optimally. And so your best option is always to play to counter whatever they're doing. So say they're betting too much, then you need to start calling more because they're probably bluffing. Or say you notice that they're not calling very much, then it's time to start bluffing more. But yeah. Um, so in conclusion, this entire research program, I learned a lot about game theory. It's always been a topic I knew about beforehand, but I didn't know very much about. So this program actually taught me a lot. Many thanks to my professor. And I also gained the experience of writing a full research paper, which I had not done in the past. In the past, I've done a specific literature review portion of a paper, but that was all I had done. So it was really interesting to, first of all, see the research process again, but also write the different sections of the paper, as well as see how you're supposed to format a paper. For example, labeling every formula, labeling every table, labeling figures is something that I've never thought about before, but I've now thinking back, always have seen in paper. But yeah, um, all in all, Eureka was a really fun experience, and I'm glad I had the opportunity to participate this summer. Thank you.